Hi friends, welcome to my channel. Today we are going to discuss a topic which is anomeric effect. So let's start. So you know that anomeric effect is very important topic as carbohydrate chemistry is concerned. Anomeric effect is also a very important topic for students who are preparing for board exams, BSc, MSc or any other competitive exam is concerned. So this video is going to be most detailed video on anomeric effect ever made on YouTube. So watch till the end, and after that I promise that you won't have any doubt regarding anomeric effect. So at first I am introducing two anomers of alpha and beta D glucose. So this is their most stable chair conformation which are in equilibrium in aqueous solution of D glucose. So here we can see the equilibrium between the two anomers of glucose. We can see from the value that the beta anomer, which is present in 64% concentration, and the alpha anomer, which is present at 36% concentration. So we know that from our previous conformation analysis knowledge that substituent cyclohexane with higher number of substituents at the equatorial position are usually more stable as with an axial substituent, as there will be no one-side axial interaction. So thus we do expect that the beta glucopyranose is more stable than the alpha glucopyranose. That's why the beta glucopyranose exists major concentration than that of the alpha anomer. But the explanation I give just now looks like a simple explanation for this observation, but it is not as simple as it looks like. There is something behind with this phenomenon. So let's talk about that. So we know from our previous knowledge that for the cyclohexane, for the substitute cyclohexane, axial conformers are less stable than that of the equatorial conformer just because of the one-side axial strain. And for the substitute pyran rings, we know that for the difference of electronegativity between the oxygen and carbon, so the bond length of carbon and oxygen are smaller than that of the CC single bond. So which brings for the pyran, the substrate group, which is R, brings the more close to those of the axial hydrogens, which increases the diaxial strain at the substrate pyran rings. So we can expect that the concentration of axial conformer for the simple substrate cyclohexane is much more, should be higher than that of the concentration of axial conformer of the substrate pyran ring, because for substrate pyran ring one diaxial strain is more severe, so the concentration of the axial conformer should be less than that of the axial conformer of the simple cyclohexane. So if this is the case, then we can expect that, well, here is another data which shows that when substrate cyclohexane, the R group is saturated by a methyl, then the axial conformer present in just 5%, and the equatorial conformer is majorly present at 95% concentration. But for the during the meter rotation of glucose, alpha anomer, where the anomeric hydroxy group present at axial position, that has a significant concentration which is 36%. But and consequently for the beta anomer, where the anomeric hydroxy group present at equatorial position is 64%. So for the substrate pyran ring, this is also a substrate pyran ring, that should be the where the hydroxy group is present in axial conformation, that should be much less, almost in the range of 1 to 5%, but this has a significant amount of concentration, that is 36%. There has to be some phenomena for which the tendency of this hydroxy group at the axial position are more than that of the single cyclohexane. And there are some other evidence also that if we replace the anomeric OH hydroxy group, which is by a more prominent electron withdrawing group, that is methoxy or acetate or such halogens like chlorine, so the alpha anomer predominates over the beta anomer concentration. You can visualize that for the alpha anomer of the methoxy substrate conformer, the alpha anomer present as 67%, and for of the glucose pentacetate, the alpha anomer exists at 86% concentration, and for the halogen, it is almost exclusive at 94% concentration. So there is something which drives the equilibrium towards the alpha anomer in spite of the axial position occurring phenomena. So the answer is the anomeric effect. So far we discussed that the D-glucose, which is we have taken one of the representative as all the ketohexose. As an example, we take D-glucose. So that exists as in aqueous medium in two different conformations, that is we call the anomers, like alpha and beta anomers, where one of the anomeric group, which is OH, remains at axial position, and one anomer remains at the equatorial position. So let's write those anomers in chair conformations. So let's remind you that this is beta anomer and this is alpha anomer. So these are the most stable conformations of both the anomers. So now we can call it this as a alpha D glucopyranose, the full name alpha D glucopyranose. Alpha stands for the anomeric designation, D10 stands for the rotation in the due to the plane polarized right, the direction, and the glucopyranose, that is glucose, denotes the name of the sugar, and the pyran, that stands for the size of the ring, the structure of the ring, which is, we know that pyran is the 6-membered cyclic ether. So we know that both the conformations has the main skeleton, which is the pyran ring. Okay, so that's why this is the pyranose. So, and similarly for this will be beta D glucopyranose. Okay, so let's just explain the anomeric effect, that what is the reason of this tendency of the anomeric hydroxyl group at the axial position in spite of the 1,3 diaxial strain. So let's just write the actual portion which is responsible for the anomeric effect, that is this position. Okay, so let's just rewrite the particular that position. So at first I am writing the alpha anomer, which is the main reason for our discussion. So why it is have significant concentration in the mutual rotation solution in the aqueous medium. So we know that oxygen has a 2 lone pair, so one of the lone pair remains at that orbital. Okay, so there will be electrons, and now for this axial bond, there we can say there is a sigma star. If it is remains at axial position, how the sigma star will be oriented? That will be oriented like this fashion. So if we take this, denotes the phases of the orbitals like this dotted fashion. So if I make this dotted as a phase, so we can observe that for the axial conformation there could be a interaction with the oxygen lone pair with the neighboring sigma star orbital, and this is the non-bonded electron, and this is a sigma star orbital of the CO bond, or you can say CX, or any group. Okay, so that when the X group will be at the axial position, that then the sigma star orbital will have some interactions which is in the neighboring vicinity, that will have some interactions with the oxygen lone pair orbital. Okay, now let's just draw the other conformation, which is the beta. The OH remains in the equatorial position. So now similarly the lone pair will be here, and now according to this bond vector or bond orientation, I will draw the sigma star orbital. Now I will draw the phases. Now there is not perfect orientations for the favoring interactions, because this will be in these directions and this is in these directions, the bond vectors. So there will be not as favorable as these orientations. So that is why the system has some interactions with its neighboring orbital. So that is why the anomeric OH in the D-glucopyranose has a tendency to remain in the axial position, which outperforms the 1,3 diaxial strain. So that is why the alpha anomer has significant concentration that are like almost 36% in the equilibrium of the limit rotation solution remains. So as you can say, if some people gives this explanation randomly, so people may not believe his ideas or the explanations. So you have to just put forward some evidence in support of that. So let's have some evidence. So I will remind you that this evidence can come in exams in forms of questions also. So let's just try to understand this with some patience. So now I will draw a structure, a cyclic structure, like this is a chlorine substituted dioxane. So here you can say this is in the cis conformation because both the chlorines are down. So we will try to write this in a chair conformation, just like the pyranose for the glucose also, because the main skeleton is like the glucose, the cyclic structure of glucose. So let's just write it. Both the groups are below the plane. So we have drawn this most stable conformer. So chemist brother provided some bond lengths. So this bond length is measured to be 1.69 Armstrong. This bond length is 1.84 Armstrong. This CCl bond length is 1.78 Armstrong. And this CO bond length is 1.42 Armstrong. So all the bond lengths, in spite of the symmetrical structure, both the CO and the Cl bond lengths are different. So let's just try to have an insight of this phenomena. So why this happens? You can say that here this is the electron, this is the anomeric, resembles to the anomeric carbon of the glucose like. So here we can imagine there is a lone pair. There you can imagine a sigma star orbital, which is in a good orientations to have interactions between the neighboring orbitals. So there will be a donation from electron density from here to here. Okay, now here if the lone pair is here, the orbital will be here, but according to this bond, if we can write the sigma star, the orientations are not perfectly oriented of the orbitals. You can have any phase according to your nature, but you can see the interactions are not favorable like this pair. Okay, so there is no anomeric effect, not anomeric effect. There is also, you can say, the anomeric effect. There is interactions, there is no interaction. So there will be, this bond will have some partial double bond character. Let's write afresh. So this bond will have some double bond character, and this bond, as this electron density is donated to the sigma star orbital, so we know that if we populate the sigma star orbital, the bond strength or the bond order decreases. Okay, and with the decrease of the bond order, the bond length also increases, and the increase of the bond order, the bond length decreases. So if the bond order of this bond increases, so bond length will decreases, and here if the bond order decreases, the bond length will increase. Okay, so if this is the with no effect case, where the CO bond was 1.42 Armstrong, and this is with the anomeric effect, the bond length is 1.39 Armstrong, because this has the partial double bond character. And if with no effect, the CCl bond length was 1.78 Armstrong, and with population donated to the sigma star orbital of this CCl bond, the bond length increases, the bond as the bond order decreases. So that is evidence quite well the 1.84 Armstrong. So this is another evidence and in the real system that the anomeric effect is happens, and this is the most prominent explanations for the anomeric effect. So now the next question comes, which is solvent polarity, that if we increase the solvent polarity, the concentration of the alpha anomer decreases, and the vice versa. Okay, so what is the reason? So as far we know that the interactions are between the non-bonded orbital, that is the lone pair of the oxygen, and with the neighboring the sigma star orbital of the carbon X group. The X group is the anomeric group which is attached to the anomeric carbon. So the interactions is that. So let's just draw a molecular orbital energy diagram. We are not drawing the molecular orbitals. So let's just draw here we put the sigma star, which is LUMO, that is the lowest unoccupied molecular orbital, and just put the non-bonded lone pair orbital, which is HOMO in this case, the highest occupied molecular orbital concerned here. So just try to visualize now, if we increase the solvent polarity of the medium. Okay, so now you have to understand that the electronegativity or the electron polarity in the orbitals are higher for the non-bonded orbitals, okay, than the sigma star orbitals. I try to mean that the electron polarity among the orbitals are higher in the lone pair orbitals than the sigma star orbitals. So if we increase the solvent polarity of the medium, so the non-bonded orbital, which is the lone pair orbital, will be much more stabilized than the sigma star orbital stabilization. So what happens here? The energy of the non-pair orbital, what I said, the energy of the non-pair orbital will be stabilized, and the extensor stabilization of the non-bonded orbital will be higher than that of the stabilization of the sigma star orbital. So sigma star orbitals will be less stabilized, and the lone pair orbital will be more stabilized. So this is the now the improvised molecular orbital in presence of increase in solvent polarity. So now you all know the increase of the energy difference between the orbital have increased upon the increase in the solvent polarity. And you know that if some interactions which is previously of a fixed energy gap, and after some effects it is decreased the energy gap increased further, then the interaction and the effect of interactions will be decreased. This is a very trivial thing. So that this effect and this orbital interactions directly connects with the tendency of the anomeric group to remain in the axial position. Okay, so if these interactions have a higher energy, then the tendency of the anomeric group will decrease to remain at the alpha position. So that's why if we increase the solvent polarity, then the concentration of the alpha anomer, the concentration of the group to remain at the axial position, will decrease. And vice versa, if we increase the non-polarity or decrease the solvent polarity of the solvent, then the concentration of the alpha anomer will increase. That means that the groups will like to present in the axial position. So that is the evidence tells the data, that this data suggests these facts, that if we treat the mid-rotation solvent in a pure methanol medium, as the methanol medium is much less polar than the aqueous medium, so the concentration of the alpha anomer will increase, and also the equilibrium constant from the beta to alpha anomer will also increase. Okay, so this can be also a supporting evidence for this molecular orbital explanation. So the next explanation is also like I have previously showed you, that with the increase of the electron withdrawing ability of the anomeric group, like if we replace the OH group in the glucose anomeric carbon with some halogens or acetate, then the concentration of the alpha anomer significantly increases. So just we will like to explain that phenomena with molecular orbital diagram again. So in the normal case, when for the OH group, if the sigma star orbital of the CO bond was here, and the HOMO, which is the lone pair of the oxygen, is here, now try to visualize that if we replace the OH, this is for the OH, if we increase electron withdrawing ability of the anomeric group, that is the group attached to the anomeric carbon, we all know that for the molecular orbital diagram, if we increase the electronegativity, then the energy of the molecular orbital decreases. So now the effect of this electron withdrawing ability will be directed to the sigma star orbital energy solely, because we are concerned, we are just increasing the electron withdrawing ability of the anomeric group, that is a sigma star orbital will be solely affected. So with the electron withdrawing, suppose we have taken a Cl for the Cl group case, the sigma star orbital will be much more energy. But the HOMO, which was located over the oxygen atom, so that doesn't have much effect or much stabilization on the increase of the neighboring neighboring groups electron withdrawing ability. Okay, this is the actual thing, and this is the obvious thing, that the energy level will not be stabilized that much, or also have, we can consider it to be identical to the previous thing. So now we can see that the energy gap between those orbitals are reduced. So as far you all know our basic knowledge, that if we for some interactions the energies are minimized from the previous due to some effects, then the interactions will be more favorable, and this interaction is more favorable, then the tendency of the alpha anomer will be much increased to remain at the alpha position. The alpha anomer concentration will be higher, and the groups tends to remain at the alpha position will also be higher. So as a result, the alpha anomer concentration will be higher. Okay, so that's why with the increase of the electron withdrawing ability of the anomeric group, the anomeric group likes to remain at the alpha position. So this is the reason in terms of molecular orbital diagram